Hi, my name is Monique Thomas. I'm a biomedical engineer and I'm our team lead.
Hi, I'm Derek Spaeth, and I'm a biomedical engineer as well as the procurement lead.
Hi, I'm Taylor Lansky and I'm a biosystems engineer.
Hi, I'm Fatma Labishi and I'm an industrial engineer.
Hello, I am Ryan Grebsmeal and I'm a biomedical engineer, and we are Phospho-Dx team 2437, and we have designed a point-of-care phosphorus diagnostic system specifically for patients with chronic kidney disease.
Chronic kidney disease is a loss of kidney function over time, which can lead to some very serious health implications. This is because in your body, your kidneys are responsible for removing waste products and control concentrations of many substances within the body, and excrete excess through urine or blood. If patients' kidneys do not function properly, then they may need to go through things like dialysis, which is the manual removal of toxins that the diseased kidneys fail to remove. But how does chronic kidney disease relate to phosphorus consumption? Well, typically kidneys remove excess phosphorus, as in high-level cases, it can be extremely toxic and detrimental. Thus, if a patient with chronic kidney disease consumes a food rich in phosphorus, their body may not excrete all of it. In about healthy patients, 80-90% of phosphorus is excreted through urine or absorbed through renal tubes. But in diseased patients, only about 50% of this is excreted or absorbed. The buildup of phosphorus can cause serious health impacts. Health impacts are mainly caused by the inverse relationship between calcium and phosphorus. Thus, when phosphorus levels in the body are high and calcium levels are low, the body will strive to reach the equilibrium between the two. To fix this imbalance, calcium will be pulled from the bones. This can cause things like bone fragility and cramps. Calcium will also need to be eventually deposited somewhere, which occasionally this is deposited in the bloodstream, which causes seizures and even in worst cases, death.
Because of the major health impacts that phosphorus can cause, we have designed a point-of-care phosphorus diagnosis system. For patients with chronic kidney disease, our system, Phospho-Dx, will give patients a peace of mind when enjoying food and will allow them to track their daily phosphorus consumption. Currently, there are a few measurement methods available like spectrophotometry and blood work, which introduces the need for our proposed solution.
The point-of-care phosphorus diagnostic system we have designed follows this structure. It consists of two main architectural subsystems, software and mechanical. Here in our system block diagram, our design can receive input from each of these subsystems, where patients may process food in the homogenizer and gather a reading from the probe to then be put into the app. Or they can simply capture an image of their food within the mobile application for further processing by our software.
The Phospho-Dx system comprises two main components, mechanical components and software components, all composed into one mobile application. The mechanical components are in a kitchen-like appliance housing, which holds the homogenizer and phosphorus probe. The homogenizer and probe can be utilized if a user wants to know the specific phosphorus content in a food sample while at home, or to test things unrecognizable by the app both from the API or the lookup table. The probe being used in the Phospho-Dx system is technically a soil phosphorus probe. We found that phosphorus probes are really hard to come by. This probe has a range of 0 to 1,999 parts per million, has a small LCD screen that displays readings, and 3 probes that work through 2 methods, electrical conductivity and utilizing ion-selective electrodes. This means that the probe can measure the conductivity of the sample and multiplies this value by a known factor for phosphorus. Initially, the 3 prongs on the probe are ion-selective electrodes that generate electrical signals that are proportional to the concentration of phosphorus ions present. From the data that we found from testing, we identified numerous limits of the probe and homogenizer. For example, liquid foods like soups, curries, sauces, beverages, or foods with multiple components. From this, we identified that the probe and homogenizer are best used in at-home settings with foods that consist of numerous ingredients like casseroles or soups and curries.
The app is split into 3 main sections, each pertaining to a different use case. The main sections include the probe data section, where users can input data from the probe and homogenizer. It also includes the lookup table, where users can search up food items from our database. And finally, the camera estimation section, where users can take a picture of a food to get an estimation of phosphorus content. Each of these main sections can then add data to the user's daily phosphorus intake graph. We will start off showing the probe data section of this app. Pressing the probe button found on the home page opens up the probe menu. The app will ask us if we want to add our data. We recommend users measure the phosphorus content of any water used during the homogenation process if using tap water at home. We will now enter our measured phosphorus data into the app. The app will now ask us if we wish to add this data into our daily phosphorus intake. We will say yes, and then the daily phosphorus graph will display this content. Next, we will show off the lookup table section of the app. Pressing the Lookup Table button found on the home page opens up the Lookup Table menu. The app will ask you to search up a food item. For this example, we will look up pizza. The app will then bring up each food item that was found for our search. For this example, we will select the Papa John's cheese pizza. The app will then display the information for the food selected and ask us if we want to add this item to our daily phosphorus intake. Lastly, we will show off the camera estimation section of this app. Pressing the Capture and Recognize button found on the home page opens up the camera menu. We will then take a picture of the food item we want to estimate, wait for the API to return this estimation data, and then in this example, we are particularly taking a picture of a banana. The app estimated that the photo taken was in fact a banana. The app will then ask if we want to add this item to our daily phosphorus intake.
Within our project, we identified several limitations. The first being that the probe is best used in situations when the patients are at home or consuming food that is full of different ingredients like soups, curries, or casseroles. If water needs to be added to make sure a food item is more of a slurry, it is best that the probe be used to measure the phosphorus content in the water being used before the food sample is added. This can be avoided if DI water is being used. Next, we identified that API struggles with things that are liquids like soups as well as branded foods. That is when the lookup table should be utilized by the user if they know what the food already is. We recommend that when taking pictures with the API to ensure that the photo captures the most recognizable features of said food. For example, if a user wants to test broccoli, it is best that the florets be dominant in the picture. Additionally, foods that have similar appearances, user discretion may be needed to properly identify the food. If the correct food still fails to be identified, it is best to use a USDA lookup table or the probe and homogenizer assembly to find the phosphorus content.
The overall spending from our project was $1,890, which led to contingency of $2,110 from our $4,000 budget. This includes the prop for the food processor and the homogenizer, which we purchased 2 versions of the purposes of prototyping.
Our first prototype was completed in January of this year, as initially we had originally planned to train our AI for our app's food and volume recognition software, but this turned to be a fruitless process after further research and consulting with individuals with more programming expertise revealed that a pre-trained AI, an API, may be effective for the timeline and scope of this project. The major change in this shift of prototyping moved our data storage from Google Cloud to requiring no storage, as the data for our prototype would be sent to the pre-trained API in the cloud and returned back to the client with the result of their food inquiry. This also addressed our volume estimation task, as volume estimation via camera is a new and developing feature of camera technology. Initially, we had researched and proposed a model involving ellipsoidal fitting of foods and imaging, or multiple image fittings. But with the FoodVisor API app containing a portion estimation feature with high accuracy, we were able to incorporate that into our first prototyping iteration. We additionally had verified and tested our food homogenizer in December. However, due to some battery and charging concerns, our team outsourced to recruit a larger outlet-powered food processor, which has been retested and verified for our project specifications. With this came the modification of our KitchenAid appliance-like housing to account for the new homogenizer and fitting. Overall, the first and last item on the agenda for our project is the app's development, which contains the essence of our project's functionality and purpose. We have been working tirelessly to adjust the features and technical aspects of the app to provide renal patients with a handheld method to manage the symptoms of their disease.